All right, welcome. Today, we're diving into a question that sounds, almost deceptively simple. But trust me, it gets right to the very heart of how we understand the fundamental forces of nature. We're going to explore the hidden geometry of reality itself.
So get this. What if the three color charges that run the show for the strong nuclear force, the glue that holds quarks together? What if they aren't just some random labels we slapped on particles? What if they're actually defined by something as ridiculously simple as the path you take around a tiny square in spacetime?
Okay, so picture this. You've got the four corners of a square. You can draw a loop that hits every single corner just once in exactly three different ways. You've got a forward path, a staggered path, and a reversed path. Now here's the big idea. What if those three geometric paths are the three colors of the strong force? Red, green, and blue. I mean, that's an incredibly elegant thought, right? But does it actually work?
So to figure that out, here's our game plan. We're going to start with this simple idea for color, then see why it hits a major roadblock in mainstream physics. After that, we'll check out an alternative theory with some different rules and see how it unlocks this whole geometric view of color. And that's going to lead us to two very different ways of looking at reality.
All right, first up, a simple idea for color. We're talking about defining a physical property from pure geometry. So let's just dive right into that core proposition. Is it really possible to get something as fundamental as color charge from nothing more than shapes and paths?
So here's the core idea in a nutshell. What if the three colors that quarks have, what if they aren't some built-in property in the usual sense? Instead, what if they're just labels that pop into existence because of these three unique ways to trace a loop? It's a really beautiful concept, right? It suggests this deeper, more geometric layer to our reality, which of course begs the question, if the idea is so clean, so elegant, why isn't it in every physics textbook?
And that brings us right to the big problem. Section 2, the standard theory's roadblock. Why this simple idea just doesn't fly in mainstream physics. See, the standard framework that physicists use for this stuff, it's called lattice gauge theory, or LGT for short. And LGT has a major problem with this whole idea. In fact, according to its rules, the difference between those paths, it's completely meaningless.
So yeah, if the idea is so simple, why isn't it standard physics? What is it about the standard model that just shuts this whole thing down? Well, the answer comes down to one of its absolute core principles.
And that principle is called gauge-invariance. Now, in simple terms, what it really means is that physics doesn't care about the how, it only cares about the what. All that matters is the final measurable outcome. The specific path you took to get there, all those intermediate steps, to physics, they just don't have any real meaning.
And this right here, this highlights the disconnect perfectly. The standard view, LGT, it only focuses on the final result. The path you took to get there, it ignores it. In lattice gauge theory, the only thing that matters is the final number you get at the end of the loop. You can think of it like a final score. And because of a quirk in the math, that final score is exactly the same no matter which of the three paths you take. So the theory sees the destination, but it is totally, completely blind to the journey.
So here's the bottom line. Within the rules of LGT, since all three paths spit out the exact same final answer, the path itself can't be a unique observable thing. The difference between them is, well, it's invisible to the physics. So in this standard view, color is just a label you attach to a quark. It's like a sticky note. It's not something that actually grows out of the geometry of spacetime.
But what if the rules were different? This is where we get to Section 3, quantum theory's different rules. We're talking about an alternative framework with a crucial new assumption. Now, this theory doesn't just throw out the standard model. Instead, it starts with one single, fundamentally different assumption, and that one change makes all the difference.
So the theory asks this really fascinating what-if question. It says, what if we fix the total topological flux to a specific value? What becomes possible then? Okay, so imagine every tiny loop in spacetime has a certain amount of, let's call it twist in it. Physicists call this topological flux. Now, what if the universe has a built-in rule that says the total amount of this twist for any given loop must always add up to a very specific fixed number?
And that is the key. Instead of just letting that twist value be whatever it wants, Qaether theory locks it in. It proposes that the universe has this fundamental built-in constraint, a setting that just can't be changed. It's kind of like saying every single game of chess must begin with the pieces set up in their standard starting positions. It's a rule. And this one single powerful constraint is what blows the door wide open to a totally new way of seeing color.
Okay, so now we get to the payoff. Section 4, Unlocking Color with Topology. Let's see how this one single rule completely changes the game. Because by fixing this topological property, those paths we talked about at the very beginning, they suddenly stop being invisible. They become physically real. So in Qaether theory, that fixed value, that total twist, it sums to a specific number, 12. And look, this isn't just some random number they picked. It comes from the deep mathematical guts of the theory. But what's really important for us is what this number does.
See, by forcing that total twist to always equal 12, the system can't just be in any random state anymore. It's forced, it's constrained to settle into one of exactly 3 stable, distinct configurations. The theory has a name for these states. They're called dihedral orbits. And here's the absolute kicker. Each one of these physically real states corresponds perfectly to one of our original 3 paths. Suddenly, the paths are distinguishable.
And right here, this is the aha moment. The theory gives us this beautiful, direct, one-to-one mapping. That first stable geometric state, dihedral orbit 1, that is the red charge. The second orbit, that is the green charge. And the third, you guessed it, that is the blue charge. Color is no longer some arbitrary label you stick on, it's a direct consequence of the underlying geometry, made physically real by this one single rule.
Okay, so let's just step back for a second and look at the big picture here. This brings us to Section 5, 2 views of reality. Because we now have 2 fundamentally different ways of understanding what color even is, and what this difference really means.
What this all boils down to is a core difference in philosophy. For the standard theory, color is an attached label. For Qaether theory, color is an emergent property of geometry. In the standard model, it's something abstract we stick onto particles. But in Qaether theory, it's something that arises naturally, right from the very fabric of space-time. It's not attached, it's woven in right from the very beginning.
So why does any of this matter? Well, because this geometric view isn't just a neat idea, it's actually really powerful. It naturally explains why red plus green plus blue equals 0, or neutral, which is a huge cornerstone of particle physics. It gives a super clear geometric meaning to anticolors. You just reverse the path. And it even explains color conservation through a fundamental geometric rule called the Bianchi identity. The point is, these aren't extra rules you have to bolt on. They just fall right out of the geometry itself.
And that leaves us with a pretty profound question to chew on. Is our reality built on fundamental labels, or is it an emergent property of pure geometry? Think about it. Is the universe built like a set of Legos, where fundamental properties like color are just snapped on as labels? Or is reality more like a complex piece of origami, where all the rich, amazing properties we see, including color, just emerge from the folding of a simple underlying geometric sheet? That right there is the fundamental choice these 2 views give us.